Sir, some highway safety modeling problems you can do.
Can we do it tomorrow? I'll try to do it tomorrow, but I'll do it in class tomorrow.
Yes, yes.
Today we'll focus on CGE models because I'm trying to figure out when we'll get the time and all, but we'll do it tomorrow. But is that something which the rest of the cohort would like as well? An example with numerical example with the HSM model, highway safety model.
I only gone through it, sir. Means what your procedure you have taught to us. Just gone through it.
All right. What we'll do today is what I want to do today is what we'll do today is go through transport network problem and the concept of equilibrium. All right. So let me share my screen. Just give me a moment. Oh, okay, okay. I don't know why. Okay, okay. Sounds good. So what I'm going to talk about today is something called transport network models. And the reason why I'm talking about transport network models is fundamentally the concept of equilibrium shows up here. How many of you have heard about the about equilibrium as a concept? Okay. So we'll go through the concept of equilibrium and what all are required in transport network models. So there are three things basically what are needed in three main inputs which are needed in a transport network model, right? The trip tables, which is the demand, which we have already spoken about over the last yesterday, I think it was. No, yesterday? 2 days back. Yep, 2 days back. We talked about demand. Then today what we're going to talk about is networks and link performance functions. All right. So what is network modeling? So essentially the way we characterize our transport network is by, you all can hear me? Can you hear me? Yeah, okay. So the way we the way we uh, the way we do network models is by first, the way we do transport models is by abstracting them as graphs, as networks and graphs. What they are is a set of nodes, and each of these nodes are actually connected by links and arcs. All right. So this abstraction actually provides us with the ability to look at, to apply standard graph theoretic algorithms like uh, shortest path algorithms, etc., um, which we will talk about. And once you've done that, you can also look at the idea of the concept of equilibrium, which we'll talk about. So this is just the terminology. You have a node, which is basically two particular things, and then a link. Now, a link is, again, going back to the idea of what a link is. A link is any uh, homogeneous section which connects two nodes. So let's say you have a national highway which is going from 4 lanes to 3 lanes. So the section which has got 4 lanes is one link. The section which has got 3 lanes is another link, and they are separated by nodes. Am I making sense? It's a very important concept when you're doing your modeling, is that you want to
Yes.
split up your road network into homogeneous links. Nodes are not only signals or merge points or diverge points. Nodes are places where the characteristics, the link characteristics change, right? You can have the same thing associated with railways as well. The link can change from a speed of 70 kilometers per hour to 30 kilometers per hour. So it's two separate links. So this is just an example. This was actually the first model. You'll see a lot of this particular network being used in a lot of uh, um, historic network modeling work, where you have this is basically Sioux Falls. So this is how the Sioux Falls network looks like, and then you abstract it into a bunch of nodes and links. All right. So then the question comes like, all right, if I have a certain OD table which is based on the demand, and I have a network, right, with link speeds, etc., and all of that, how do I determine the link flows? How do I determine how many vehicles will take each link? All right. So that is the question which we have. Now, again, there's a reason why I'm bringing this up, because the concept of equilibrium is fundamental to the next class we're going to do around computable general equilibriums and economic equilibriums. All right. So the way we end up doing this is going back to a fundamental assumption. How do people choose routes? How do you think people choose routes? Exactly. So people take the shortest route, right? So so people take the shortest route, or they take by either by travel time. Generally, in our case, when we are doing a lot of these equilibrium problems, it's based on generalized cost, where we convert money to uh, uh, money to um, money to time, or time to money. So we convert that into a cost. So now what happens is, if everybody takes the shortest travel time, what will happen? The travel time will increase because of congestion. So then people need to will take another route. So this is the concept of equilibrium. The equilibrium is when the travel time on all used paths between an origin and destination point are equal, and less than that experienced by any other vehicle on an unused path. So if you take an OD, right, let's go back to this model. I want to go from here, A, to this point here, right? There are multiple paths. You can go like this, you can go like this, you can do a milk run from between the city. You can also come down like this, and you could also have this route. So let's take 3 routes: this one, and this one. So the concept of equilibrium is, if I want people to go from this origin to this destination, the travel time. So if, let's say, this is the shortest path, if everybody takes this path, congestion will increase. It will be quite the travel times will increase. So some people will move here. People will move here until the travel times are equal, right? Because now the reason why travel time is equal is important is it is only on the used paths. You also have this path here, right? You have this path. This is an unused path. So there'll be no vehicle on this. So the travel time is much larger. So the idea being that the concept of a transport network is said to be at an equilibrium when the travel time on all used paths are equal, and on all unused paths are greater than that of the used paths. Am I making sense here? This can also be rewritten as no traveler can improve the travel time by unilaterally changing routes. Any questions? Any questions? Okay.
No, sir. No, sir.
All right. So then we have the concept of equilibrium assignment. It is a very, we can, I'll give you a intuition behind it. And I already gave an intuition behind it. The idea being that first you assign everyone to the shortest path. Then you find the shortest path after you do that. If it is the same one, then you're done. If it is not, then move some of the vehicles from the current shortest path to the next one, and keep moving between these different vehicles, between these different roads. That's essentially what is happening till convergence happens. So the idea of convergence is when all link travel times are equal on all used paths. So let's take this example. You have 6 travelers coming here and 6 from this 1 to 4. All right. And your travel times are given here: 50 plus x, 10x, 10x, 50 plus x. How will people reroute on this? What is our initial cost? This is 50. So if there's no vehicles, this is 50. 10x is 0, x is 0. So x is the number of vehicles. So this is 0. So the travel time here is 50. Travel time here is 50. So first we'll assign all these 6 travelers to one of them. Let's assign them to the first one. So this becomes 56 plus 60. Correct? That is 116. And this one is only 50. So we'll take some of the vehicles from here and move it down. So eventually you'll find that 3 vehicles need to go up and 3 vehicles need to go down. Right? So you put each one, and then you'll notice that as you come down, you'll find that the accessibility metric is 83. So 53 plus 30 is 83. Any questions so far? No. So once again, what you can actually notice is that according to Wardrop's equilibrium, no traveler can improve their travel time by unilaterally changing their routes, right? Now let's take another simplified model. We have two paths, right? ABD, ACD, and there are 46 people who want to go from A to D. How will they? We did this the thing. So how they are very symmetric, right? So this is x1 by 10, 5, 5 plus x4 by 10. What do you think would be the? How would people split themselves on this route? What will be the equilibrium solution? What will be x1 and what will be x4? Any thoughts?
Can we find some in a linear equation format?
Yeah, you can do
A
that as a linear equation
x1
as well. So x1 by 10 should be equal to x1 by 10 plus 5 should be equal to 5 plus x4 by 10. And x1 plus x4 should be equal to 46, correct? So, so the first equation tells me that x1 should be equal to x4, right? So 2x1 is equal to 46. So x1 is equal to 23 and x4 is equal to 23. Right?
Yeah, yes, sir. Yeah.
So that what will be the total travel time on this? That will be 4.6 plus 5, 9.6. Correct?
Yeah.
Now tell me if I had changed my travel time. So no, it's not 9.6, it's 2.6. So 23. 2.3 plus 5 is 7.3. 7.3. Okay, I'll give you another example now. Let's do this example. Let's assume that ABD, BD is not 5 but 10. How will your linear equations change? Can you solve that?
Or it is 12.3 approximate.
Let me open new document. So what we get is x1 by 10 and it becomes 10 plus x1 by 10 is equal to 5 plus x4 by 10. Correct? I've converted this 5 to a 10. So this becomes this equation will become x4 minus x1 is equal to 50. Correct? But we also know that x1 plus x4 is equal to 46. If I solve these two, what should this become?
X1 is equal to 4.
2x4 is equal to 96. Correct? 2x4 is equal to 96. So x4 is equal to 48. And x1 is equal to minus 2. What has gone wrong?
Does it mean that for both the paths, the travel time should be same?
Can you say that again, Monica?
For both the paths, that is ABD and ACD, the travel time between submitted as T1 is equal to 10. So in both the cases, it should be 5, 5 because we changed it to 10 no? Only
Yeah.
for ABB.
So what does this mean? What do you think it means? Can you just say in one line, what do you think has happened?
That one path is longer, so and the another is short. So travel time taken is the larger one.
So yeah,
Basically,
so in a lot of sense, if if all these 46 people took this, right, it would be 9.6. The travel time would be 9.6. But the travel time here is only 10. So what is the fundamental this thing? What is the equilibrium principle? The travel time on all used paths between an origin and destination points are equal and less than those which are experienced by a single vehicle on any unused path. Or no traveler can improve their travel time by unilaterally changing their routes. So whenever you get these results which are negative or greater, that means you're trying to push vehicles on a road where the travel times are larger. So the equilibrium solution would be just all the vehicles would be taking this route, ACD. Is that what you were saying, Monica?
yes, sir, exactly.
Yeah, perfect. So, so, so when you're doing, whenever you're doing these linear equations, be careful about negative results or these kind of counterintuitive results. So I just wanted to because we did that, I wanted to just pose it to you that that's something which you want to do. So
So can you take the practical example for this is one year
I can't really
this
hear you well, Monica. There's a lot of background noise. Sorry. Can you can you write it? I'll try to listen to. I'll try to pick it up on the. Can you just put it on the message because I can't hear. There was a lot of traffic noise. Can we say the example is of a one way? Yes, absolutely. But in a one way, usually what you would do is you would close out the other, like you would not allow road. So the travel time on that road would be infinity, right? So you would not allow for people to use that road. All right. Okay. So going back to the original problem, 23 people will go on top, 23 people will go down. So that will be 2.3 plus 5, 7.3, 5 plus 2.3, 7.3, right? Now 7.3 is what? Uh, so yeah, so that's 7.3. Now what is the travel time on AB and CD? So the travel time on AB is 2.3, travel time on CD is 2.3. Now BC is very, very close. There was a river flowing through it, and AB, like BC is very, very close. So it kind of almost comes down. So a politician looks at this and says, oh, there is 2.3 here, there is 2.3 here, 4.6. So if I build this road here, right? If I build this road here, then I can reduce the travel time by almost 2.5 or 2.7 by 2.7 minutes. So they put this link. Now this is zero. This travel time is zero. It's a big freeway and it's very close. So it's just literally putting a bridge. What do you think will happen now? So because this is 2.3 plus 2.3, that's 4.6. People on this road will move here, right? So let's say everybody moves here. So this will be 4.6 plus 4.6, that's 9.2, right? That's 9.2. Now, is this an equilibrium? So if you look at this, this is 4.6, which is less than 5. And this is 4.6, which is less than 5. So there's no reason why anybody will change their routes, right? So this will be 2.3 plus 5, which is 7. No, 4.6 plus 5, which is 9.3. And this is 5 plus 4.6, which is 9.3. No, 9.6, sorry, 9.6. 4.6 plus 5 is 9.6. And this one is 9.2. So now what you've done is by just building a new road, right? You have increased the congestion to 9.2 from 7.3. And this is called Bayes paradox. And that's why network equilibrium, that's why we do a lot of this network modeling. It's because just because you're building a new link or building a new transport link doesn't mean that it's actually going to improve your congestion. It can actually make it worse, because at the end of the day, people are trying to minimize their travel time, and because they are myopically minimizing their travel time, they end up in a local suboptimal solution. So local suboptimal system solution. So the only way to now improve the system is by not allowing people to use this bridge. So you make it a walkway, and you see that right in Delhi also. Once there are certain sections of Connaught Place which have been removed, like where have been made not for traffic. So you remove that, and then you end up with a better equilibrium. Any questions so far? Is it making sense?
Yes, sir. But sir, how we can predict the public transport in this case? Means the
How can we?
bus route or the public transport, means BRT or such type of.
So there is something called the Down-Thompson's paradox.
Okay.
Just give me 1 second, please. So there's something called the Down-Thompson's paradox. In Down-Thompson's paradox, what they did was there's a road and rail choice, and they improved the road, and the whole system became worse.
Okay. Now, are you mentioning now if you are increasing in any link or any updation in link, there will be not affected your model. But in case of any BRT route we are proposing in our urban area,
Yeah.
so in that case, there will be how we can interlink that concept with this example or this concept.
So generally what you have is in the traffic assignment, it's traffic, but you also have a mode choice, right?
Yeah.
So you're doing an assignment on the link. So what you would generally do is you would have a link which only allows for buses.
Right.
So you can do links which only use buses, or which can only use pedestrian, which can only use cycling, and you can redo this entire analysis. So this is just a simple one. So you actually expand the concept of a network and an abstraction of the network to include other modes.
Okay.
Any other questions? So this is why we end up having management. And these things can grow exceptionally large very quickly. Now, one of the interesting things about these paradoxes, so you can go and read about this. So the Bayes paradox is one. There's also an information paradox. So one of the things is, if let's say this was an unreliable link, And here you provide information that whether or not this link is going to be used, is bad, good or bad. What ends up happening is sometimes providing information actually also reduces the performance of your network.
Yeah, what it's so V by series also decreases, right?
Yeah. So that's so now the only thing we did was static, right? The next step is called dynamic. So you can start having the concept of dynamic models. What is a dynamic model? So what a dynamic model does is it incorporates the travel time of the next time step. So you have a total. So if we looked at this, we had 46 people going, and each of these 46, every one of these 46 would experience the same travel time of 4.6, irrespective of when they join the queue. Correct? But usually the last one experiences the most congestion. So that is what the dynamic assignment tries to take care of. All right. So path 1 has a travel time of 10 plus x seconds, and path 2 has a travel time of 15 plus x. So on path 1, so static case, path 1 will have 505 vehicles and path 2 will have 495 vehicles. Now let's assume that there are two time periods, 400 vehicles and 600 vehicles over a 10-minute interval. So the first 10 minutes is 400 vehicles, the second 10 minutes is 600 vehicles. Okay. So the first 400 vehicles go. So how will they split themselves? So this is, they'll split themselves based on 205 and 195. Okay. There's going to be a difference of 10, basically.
Yes, sir.
Yeah, so 205 will take this, 195 will take this. The second time it will be 305 and 295. Now, if you look at the total proportions, 205 plus 305, that is 510. So 510 is greater than 505. So your distribution of how people, if you have dynamic traffic assignment, because people are reacting to the travel times later on, right? They end up redistributing themselves very differently as opposed to a static one. So one might ask, why don't we use dynamic for everything? Why are we using static? Static is generally used for long-term planning. So we are interested in averages. We are not interested in actual travel times, what will happen in the next 10 minutes, next 10 minutes, next 10 minutes, etc. Any questions?
So in this case, we are creating the scenarios, multiple, right?
So every travel, we are not creating multiple scenarios. In a dynamic traffic assignment, every time step is independently, not independently, is every time step, the way people would actually reroute would depend on what has happened to the network in the previous time step.
Okay.
Yeah.
With the reference of before, we
Yep.
will proceeding after.
Correct. So we actually did this. We already talked about the idea of algebraic approach. So, right. So 2 plus x1, 1 plus x2, 1 plus 2x2. We solved this, right? So, now if we add a new link, it'll end up with, you basically end up with multiple, you end up with uh, multiple equations, multiple simultaneous equations, which you're trying to solve. Now, just always remember that you always need to check whether the travel time on an unused path is greater than 0 or not, greater than the current travel times. there are that is one piece which is problematic. The second piece, which is really hard, doing the algebraic approach. Algebraic approach is easy when you have a network where the paths are well defined. But when you have this, let's go back to this network. This network going from point 1 to point 18, let's say, enumerating all paths, all possible paths, is a very, very hard problem. It's actually, it's known to be an NP complete problem. So knowing that you have actually got all the paths, so you can have a path which goes 1, 3, 4, 5, 6, 8, 16, 18. You could also have taken 8, 7, 18. It is a really, really exponential problem, enumerating all the paths in a network. Because if you're going to take an algebraic approach, you really need to enumerate all your paths. And you need to enumerate all paths from all ODs, not just one OD. Right?
Yes,
Any
sir.
any questions on this? So that is the second issue with actually doing a path enumeration. All right. This is basically doing it the algebraic approach. It's the path enumeration. So generalized systems can be used to algebraically solve if a path is used, demand conservation, and flow conservation. So no vehicles are lost in the world. But the problem is actually being able to. So one piece is finding all the paths, right? Travel cost. So this is the travel cost. Many possible link cost functions, most have this form, right? So what a link performance function tells you is how is the travel time changing with link flow. So that's basically the idea of V by C. And we use usually for static, we use the idea of the BPR function, which is called the Bureau of Public Roads. It is 50, 60 years old now. It's a 60-year-old equation. And the reason why you end up using this is because it is independent for each link. It is convex, and you can use this. This has some nice properties when it comes down to the idea of convergence, the concept of uniqueness of flows on each link, etc. All right. So T is equal to T naught, which is the free flow speed, and this is the V by C ratio. Any questions? I think one question which people have, and I've kind of just brushed over it. One, we do know that this is an unrealistic model, all right, for two reasons. One is the volume can become greater than the capacity, right? V by Q, V by C. Q is the capacity, so it can be C. Your volume to capacity can be greater than 1. But in reality, we know that doesn't happen. The second thing why it is also unrealistic is the concept of Q spillback. Because these are independent travel time functions for each link, right? Each link has its own travel time function. Just because you have if you have a congestion in the link in front, it doesn't mean that travel time actually that congestion actually spills back to the link before. That doesn't happen. So those are the two reasons why these are actually not realistic, but they're useful. They are useful because they provide you average travel times on a network for static conditions. Second thing is because they're convex, right? Like this is a convex function. They provide nice mathematical properties around equilibrium. One, it provides that it guarantees that you're going to have an equilibrium solution. The second thing is it also guarantees that the volumes on each link are unique. Every time I run my for a given OD matrix in a network, if I run my model 10,000 times, it will always give me the same volume. That is the reason why we chose this, because having a consistent prediction of volumes from an equilibrium is important. Any questions?
Sir, are you mentioning the prediction in volume? How we can predict that volume? Did not get that point. V by Q.
Can you say that again?
Sir, are you mentioning now we have predicted the volume for
So when I say predicting the volume, when we do our equilibrium, right? Like we run the equilibrium, like let's say the algebraic approach, we do the x1 plus x2 and we solve it. We have actually solved the volumes. Solved. So but that's what I mean by predicted. We have determined what the volumes are.
okay. So it is not assumed. It is by
It's not assumed.
okay.
It's not assumed at all. So that's it's everything like we did before. So these
All are
all these volumes
in.
are not assumed. These are solved for.
Oh.
We solve for volumes.
Yeah.
This equation
Hmm.
is assumed. We
Oh.
will have a parameter q, a parameter alpha and parameter beta, which are calibrated for, which are assumed. All right.
Hmm.
But then we solve for volumes.
Oh.
So this is just giving you an example here, right? This has a free flow speed of 20 minutes. This one has a free flow speed of 10 minutes. But this one has a low capacity of 2200. This has double the capacity. It takes longer but has double the capacity. And this one has a lower capacity. Solve for this. Usually you end up taking alpha is equal to 0.15, beta is equal to 4. So you can solve, like literally it's an easy solution. So what you'll end up doing is you'll find that twice of x1 divided by 4400 raised to power 4 should be equal to x2 divided by 2200. So that means 2 times x1 by 2 raised to power 4 should be equal to x2.
Okay.
Right?
Yeah.
So x1 is fourth root of 2 times x1 divided by 2. So basically x1 raised to power 4. So x1 divided by x2 should be equal to 2 raised to power 3 by 4. That is 1. And x1 plus x2 is equal to 7000. If you solve, so if you just take the ratio, so if you take this travel time should be equal to this travel time, you'll end up with a equation which you can then, yeah. So any questions so far?
So, sir, there will be any check now how means this model we can run it in any software. There will be how we can check means we are going in a proper manner or there will be any
So
misunderstanding.
very good question. So the check is always going to be this. So
Okay.
so whether or not, so if you're modeling it as an equilibrium problem, you have, this is the first check. Okay,
Okay.
this is
Okay.
check one.
Hmm.
Then the second thing is you want to be calibrating and validating the model also. So you want to make sure that the volumes you're getting. So, and that's when I said, if I go back down here, if I go back down here, if I go back down here, if I go back, what was I going to say? Yeah, no, this is where I wanted to go down here. So alpha, beta, and Q, right? The capacity. So capacity is if you have got 2-lane road, or if you've got a 1-lane road, generally it's 1,200 PCU per hour, right? So you'll put, so then you multiply that by the number of lanes, you get a Q. Or you choose your alpha and beta as alpha is 0.15, beta is 4, and then you play around with your Q. So what you're trying to do is you're trying to, given an OD table, you're trying to make sure that you're getting the travel times to be what is expected today. Okay. So that is a part of one of the parts of the calibration. And then the validation is making sure that the travel times are coming out to be equal, right? So we talked about this, right? Like algebra helps for small examples and often relies on repeatedly solving the shortest path problem, right? So you do the shortest path problem, move a little bit here, and then you move things around, and then you create a scalable method. So you calculate your path travel times, find shortest paths, adjust path choices towards equilibrium, and calculate path travel time. So this is basically the iterative framework in through which we work through.
Yes.
All right. So one thing, again, going back to what is correct, like checking whether or not if things are coming to a solution, is the idea of convergence. All right. Convergence tells you whether your travel times are converged or not, whether you've come to an equilibrium or not. So let's go back to the concept of an equilibrium. The concept of an equilibrium is that the travel time on all used path should be the smallest, correct? So what we do is we take the total system travel time. So we look at the travel times of all the vehicles in the network. That's my total system travel, add them up. Then I take each OD and multiply that with a OD trip, and I multiplied that with the shortest. So DRS is the total, the trips between origin R and destination S. TPRS is the shortest path between origin R and destination S. So, and then we divide that by this. If every vehicle is taking the shortest possible path and cannot converge, this should come down to 0, right? So if I take an off equilibrium, so let's take this example itself. There are 5 vehicles going from here, from 1 to 2, and you have x1, x2, x3, right? Like, so these are the, I don't know if you can see this. The travel times on this is 2 plus x1. This one is 1 plus 2 x2, and T3 is x3. All right.
Yeah. Yes.
So, okay. So now let's take an off equilibrium. When I say off equilibrium, an off equilibrium numbers. So you have 2, 1, 2. All right. So what is that? This will be 2 plus 2, 4. This will be 2, and this will be 2. All right. So 4 times 2. So this was. We will get to that. So that is 4 times 2. This one is 4 times 2. This is 3. This is 1 times 3, right? And this is 2 times 2. So 2 times 4 is 8, plus 3, 11, plus 4, 15. Okay. Now, what is the shortest travel time? It was 2. So all these 5 should have taken 2. So that is 10. 10 minus 5. 10 minus 15 is 5. 5 divided by 15 is 3. 1 by 3. That's 0.33. So the gap is large. So you're 33% off from your equilibrium, some equilibrium. Now, the equilibrium solution is 1, 1, 3. So you take 1, 1, 3, right? So that will be 1 times 3 plus 1 times 3 plus 3 times 3. So that is basically 3 plus 3, 6 plus 9, 15. And 5 times 3 is 15. That's equal to 0. So at equilibrium, your gap is going to be 0. Usually, you try to get your gap to be less than 5% or less than 1%. It's a very important criteria which we try to do through our modeling, is getting to this. How do we know are we at equilibrium or not, particularly when we have big networks? Does it make sense?
Yes.
Does it make sense to everyone? I think only Manish is been saying yes, and I'm glad that Manish is saying yes, but I feel like I'm only teaching you, Manish. Vikas? Yeah, Rahul, tell me.
Yes, sir. Understood, sir. That's why
Okay,
I
perfect.
waved the hands.
Okay. I thought you were raising your hand. All good, sounds good. So then there are a lot of algorithms. There's a method of successive average, Frank Wolf. I'll not be covering in this thing. There are other approaches. There's gradient projection, algorithm B. There's TAPIS. Lots of such algorithms moving forward. So this is an example of the Greater Sydney model. In fact, one of the largest models that has been ever built for not for macro models, but for meso models. No, yeah, meso models is for Delhi. It's the largest model that has been built. And it takes days for it to converge, All right. In fact, the CGE model we have built for India is the largest known as well. And it used to take us 2 days, 3 days for it to converge. Now it takes, we will talk about that later. So this is the network composition. So there are 58,000 links, 20,000 nodes, 2,282, 1 million vehicle demand, 1,159 bus routes. So, all right. So there are two pieces here. I'm just giving you an example. So we compare. So when we are doing the calibration, right? When we are doing the calibration, one of the things we try to do is get the GH statistics less than 10 or less than 5. 85% of them should be less than 10. So this is the GH statistics. So it's telling you each of these, which are the points where we have some counts around the travel times and travel volumes. All right. So we are making sure that the travel volumes are less, are convergent. Now in this area, this is the CBD area. This is giving you the volume to capacity ratios for the 2-hour period. And we end up doing an entire traffic simulation model here around the meso model. And so this is not, and for each one, so I'm talking about the GH static, this is for the calibration to make sure that what the model is producing is the same as what we are observing in the real world. But whenever we run the model, we are making sure that the convergence is less than 0.01, less than 1%. And then once we get that, we get outputs. So you can look at what the travel times are, what the volume to capacity ratios are, which areas are congested. So this is basically, this area is the CBD. This is of the CBD. We have, so yeah. If any of you ever want to come to UNSW, our university is here, this part. Any questions? Yes, Rahul.
So, sir, how we can predict the means TAs means upcoming generation model? Means for example, this is model for year 2020-2025. The same model we can run for 2050, 2070. So we can update the model or else we can change the volume data.
So let me go back. I'll go back right. So any transport model needs these three things, right?
Hmm.
Now you need to figure out what your policy changes are and how things are going to affect in 2050. So one thing which you have to change is your trip table. You have to do a forecast on your trip tables. Now some people say that all right, you just increase the OD by 20%, 30%, 40%. For by 2050, it would have increased by 30-40%. But there's also changes that are happening on land use, correct? Like
Yeah.
some areas might become residential, some areas where there is nothing will become commercial. So there is something happening. So because of that, your OD table might change itself. So you have to do an entire OD estimation piece as part of your forecast for 2050. You'll have to do that, correct?
Yeah.
Then the network will change. So the network, you're going to say that how will my 2050 network look like? What will be the capacity? Where all will be the metro rail? What will be the trains? All of that, and you'll make that change. Okay.
Okay.
Then the last one is the link performance functions. Now, this is what you have calibrated for today, is the link performance functions. So you would have gotten that. You can put that for that time. The second thing you can do also for the link performance function is you might say that, look, one thing we believe is autonomous vehicles are coming. We are going to have more electric vehicles. So the link performance function might change. And that is okay. But you make that change. But you have to explain why each of those changes are being made to each of those pieces. And people will fight you. Like when you start presenting this data, right? People are going to say, look, why are you using this trip table? Why are you not doing? And what will happen is they would have told you in the previous meeting that you should use this trip table. Next meeting you come, they'll tell you should use some other trip table.
Yeah.
All right. In the previous, they'll say why they are planning this road. Next, they'll say, why did you put this road?
Right.
So you're going to face that as a planner, as a modeler all the time. Like because you go, there will be a decision maker they have their own minds.
Right.
Now, the way to solve for that is do a lot of scenario testing. Say that, okay, yeah, we have already done that. This is how it looks. We have already done that. This is how it looks. We have already done that. This is how it looks. So based on all of these, we think this result is the most robust result because people are trying to find the reason why. There are two reasons. One is when we are irritated, we just say that they don't know what they're asking. They don't know what they want, so they're making us do all this other work. But essentially what they're looking for, if you're a little bit more kinder and if you think about what they're really looking for, is they're looking for a robust solution. They are looking for a policy solution which is robust across all these different scenarios. And in their mind, these are the different scenarios. So if you have done that analysis before, it shows preparation.
Yeah. Got it.
It is a very, very important step for this thing. Because otherwise, it becomes a very confrontational and very irritating process if you don't go prepared.
Yeah, sir. Actually, I have gone through faces some type of issues problem. Currently, I am working on Ahmedabad airport
Okay.
erection project. So, so
So
all.
so one of the things with all these real projects is that already somebody has a solution in mind. Okay, the first thing is that
Yeah.
somebody already knows that they want to do something there.
Right.
So put that into your network. Then there will be then do sensitivity analysis. Okay, we will put a metro, we'll put this, we'll put that. Then there'll be a discussion. Okay, metro is too expensive. We don't need to worry about that. So, but the discussion will not be about, oh, you have not modeled. You do
Yeah.
all the potential models. Do that. It will save you more number of meetings. Because the hardest part of developing a model is the calibration and validation and development of the model. Okay, that is the hardest part. Putting in scenarios, do as many as you can go as you can before you end up in the meeting.
Yes. Got it.
Excellent. So this is a traffic assignment. So I've talked through this. So dynamic traffic assignment is when you're actually looking at travel time slices. So you have OD travel time. So this is all. I think we have talked a lot about macroscopic, mesoscopic, and microscopic. The main places where they actually are different is the. I'll go back up here. You know where the biggest difference between macroscopic, mesoscopic, and microscopic is in all of this?
As per my practical experience, say that when we develop any city, for example, that time we are doing the microscopic. Yes.
Yeah. But let's go a little bit more. So you're telling me where you want to be using different simulation models. But I'm asking a more abstract question. If you have a macroscopic, mesoscopic, and a microscopic model, where is the difference? Because if every model has a trip table, a network, and a link performance function, where is the difference between these three?
The difference will be seen in the microscopic simulation models, because we are
No. So again, you're telling me, so even the mesoscopic is very different. But
okay.
I'm asking in these three categories, like trip table, network, or link performance function, where is the difference? Like what makes models different?
Link performance function.
The link performance function. Macroscopic is static. Mesoscopic is dynamic. Microscopic is vehicle. And that's what I want to kind of, so that's how you want to be thinking about it. Is then you ask the question, okay, the differences in all of these models is only on the link performance functions. So where does in which type of project I need what type of link performance function? That's the question you should be asking.
Okay.
So when you're doing small intersections, small pieces of cities, you use microscopic because you want to pick up on the interaction. Correct?
Yes.
So this is a macroscopic static model. We have talked about this. So there's no dynamics, there's no queuing spill black. It's used for strategic level planning, prioritization, and forecast. Then you have mesoscopic model. It's used for dynamic message signs, tolling, information, signal systems, and it basically uses flow density curves. It says that on this link, given the density, this is going to be the speed. All right.
Yeah.
That is usually what it is doing. Then microscopic is actually doing car following, lane changing, and it is looking at interaction between the different vehicle types. So now this is long time ago. Aimson used to provide a macro, meso, micro. You can actually do a micro simulation model, then go to a meso and macro as well. There are other places as well which are doing this, like Vissim PTV also provides you this opportunity. So the final thing is always remember, so in all of these questions, each of these models provide you different level of precision and different level of accuracy. And the way we have tried to articulate this, right, like is people ask for people say that we are looking for accuracy, but what they're looking for is precision. Okay. Precision is that you can be very inaccurate, but everything is in tight. There's very little error in your results. Like error, there's a lot of internal consistency in your results. But you can have a high level of accuracy and low precision. So like a static model is, so you're basically kind of figuring out where you want to be in this. Okay. So with that, that is my discussions about equilibrium network models. And now we're going to expand it into CGE. Any
Yes.
questions?
Sir, I have one practical. Yeah, please, because. Sir, I have one practical question. Actually, I do a macro simulation on Vision software for any base year. For example, year 25, for example. So I got an level of service E or D for year current year. So I can increase the lane configuration of particular junction. I improved. I provide the island. Also provide the signalization on the particular junction. But as well as our year will be increases. Our traffic also our traffic growth traffic rates is also increases. So the increasing in geometry or the winding of geometry, it is not a proper solution to it is not a proper solution to smoothly traffic congestion to resolve. So how we can as transport planner, how we can think accordingly that to in upcoming year, how we can rectify that traffic problems. Means winding of road is not a solution according to
So
the
what do you mean by winding of road? Can you?
for example, current is 2+2 lane road configuration. After the 5 or 6 year, we generalize the traffic congestion rate is more, so we can expand one more lane. So 3+3. After 5 6 year, also we think that it is not sufficient. So also we are proposing to flyover. So it is not a permanent solution, na, sir. So what, as a planner point of view or as a modeler point of view, what is our thinking scenario or view to tackle this practical problem?
So one of the things about it is, it, like all of these traffic congestion problems, it is born out of multiple reasons, right? First of all, you want your economy to grow, so you do need better roads, you need to provide better connectivity, and you need better travel times. So that is one. So you build that. Now, the second piece is you need to be, a lot of this is actually determined at a planning level from a zoning perspective. Like if you don't do appropriate zoning, right? Like for instance, you want to be making sure that uh, let's say you have a CBD area, but the CBD area also is doing a lot of heavy equipment production. So there's going to be a lot of freight coming in and out. So that is going to create a congestion with the normal traffic. But if you say that, all right, we don't need these production facilities inside the inside the
Zone.
inside the CBD, we
Okay.
zone them outside. You might be able to actually create better uh, and more conducive environment for traffic. So you really need to look at it more holistically as a zoning problem, and then also think about other modes, right? So one of the things which larger cities have done very effectively is make uh, make um, provide alternatives, very good connected alternatives like metro, rail, etc., and public transport. But the second thing is they are actually inducing, they are actually introducing and inducing appropriate cost to vehicle. So what that means is you do congestion pricing, you do actually appropriate parking pricing as well.
Yes, yes, sir.
So then what you're doing is the moment you start doing that, right, people move to
Public transport.
public transport, but not because you want people to move to public transport. You're doing it because you're actually recognizing what the actual cost of maintaining and keeping such a system is. So in fact, going back to the Braze paradox, right?
Mhm.
Let's go back to the Braze paradox. If I had put a toll, I'm just going to share my screen again. So if I look at this,
Yes, sir.
we basically ended up with a total travel time of 9.2 minutes, correct?
Yeah.
So now if I had charged, let's say $1 is equal to 1 minute. Let's assume that is $1 is equal to 1 minute, right? This was 7.3 minutes.
Hmm.
So if I had charged $3, right?
Hmm.
If I had charged $3 here for people wanting to go from here, I would get back to the original user equilibrium. So if the moment you charge people
Mhm.
the right cost associated to the marginal cost of change, right? So that's one of the things. So in congestion pricing, you have this idea of marginal cost tolling. So for every person, what is the additional cost they are inducing on the network? So by introducing this new road, I have induced a marginal cost of 7.3, 1.9 minutes.
Yeah.
So if I charge 1.9 minutes or $1.9 here, people will move back.
Yeah.
Yeah.
Yeah. Yes, sir. Got it.
Also. Any other questions? Any thoughts? Perfect. So let's take a 15-minute break and we can, we can come back and we'll do the CGE modeling piece after this. The CGE modeling piece is a little bit more mathematical, but and a more, it'll be a little bit more technical, but we will spend time on it. And then after that, this evening, um, uh, we will do an example of using it. You all have access to laptops?
Which, sir?
Do you all have access to laptops today? In the evening, please get yourself an access to a laptop or a computer so that we can,
Yeah.
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 Sounds good. Thank you. Okay. So what I'm going to talk about now is going into computable general equilibrium. So what we studied so far was the concept of equilibrium in traffic, right? But
Yes.
the whole idea of an economy is that the economy is coming. There's a concept of equilibrium in the economy. So usually the way we set up our equilibrium is that let's take this example. You have a supply curve and you have a demand curve. And what it tells you is, for a given supply, what will be the different demand, and that gives you a different equilibrium. So in an economy, the prices are what we solve for. So if you have a certain supply and a certain demand, how will the prices equilibrate, so that the supply and demand would get uh, uh, the demand would get satisfied by the supply. The second thing in that is it becomes really complex, particularly because there are different sectors of the society, economy, and each sector is using part of the other sector. So for instance, the manufacturing sector will be using commodities from steel, right? So they are a demand, but they're also supplying, which then goes to which ends up supplying to the mineral sector. So there's an entire there's a lot of the word would be interdependence across the different industries. But also then you have households. The households are the consumers of these products which are coming from the industries, but also they provide labor to the industries, and then in turn for the labor they provide money. So consumers provide two things, households provide two things to industries, right, to producers. One is labor, the second is capital. What is capital? Can anybody tell me what capital means?
Investment capital.
Yeah, exactly. The savings from the households goes there. Industries also have their own capital, which they provide to other industries, but they also provide money in turn for labor, and provide commodities which the consumers use. So what is CGE? CGE stands for computable general equilibrium. Okay. Computable because you should be able to compute it. General equilibrium because you are finding an equilibrium across industry, households, and different parts of the society. And transport plays a role in this. So imagine if 30% of the cost of a commodity is because of logistics, because of movement, then any reduction in travel time or reduction in the cost of travel would affect the price of the commodity, which would then affect the demand, which would then affect the supply of other things, right? So this is what it's trying to do. A CGE model tries to simulate the production, distribution, consumption process in an entire economy with a set of nonlinear equations. And we'll talk through these equations, which represents the supply and demand in the market. And we say that the market is in equilibrium if the supply at a certain price is equal to the demand at that price. So what you're trying to do is trying to find the prices such that the supply is equal to the demand across all the commodities and across all the households and firms.
Yes, sir.
So the macroeconomic, so the whole CGE model was initially used for taxes and labor policies, and also around investment decisions across the different sectors. So transport networks basically play an important role in all of this, and that's what we are trying to capture. Okay, any
Yes,
question?
So, sir, in this case, we are only think about what is our investment of particular project, right? Or vice versa, investment as well as revenue.
So it has more to do with the general benefits of that project. So we are not looking about the actual investment of that. So we don't look at the cost. The cost is a part of the cost. But the CG model actually looks at the benefit. So once the road comes in, what will be the impact on the logistics cost? Because of the logistics cost, what will be the impact on the prices? Because of the prices, how much has the production increased? Because of the production increase, how much has the demand increased? And what is the welfare? Where are the jobs being created because of the production increase? How much is the income increase in these regions? All of that you can get.
Okay.
Does that make sense? So if you
Yeah.
go back to our discussions yesterday around economic impact assessment, what we are doing, the CG model tries to do is tries to provide a systematic methodology for characterizing wider economic benefits.
Okay.
So what is the structure of this? So essentially what households do is households have a utility.
Sir, one
Right?
request to can you please full screen it?
Oh yeah.
Yeah. Thank you.
So there are two major entities in this CG model. One is households and the other is industries or production facilities. Households have a utility which they're trying to maximize. That utility is derived from consumption of different activities. It could be apples, oranges, movie, all of that. And the second part of it is leisure. They're also trying to, like, people want to spend around 8 to 10 hours. So if you have a 24-hour day, they want at least 10 hours, 10 to 15 hours of leisure because they want to sleep as well. So there are constraints around the amount of time as well. So like leisure, and so the time spent on leisure versus the time spent on working should be equal to 24 hours. Okay, so that is one constraint you have. Then you're also consuming from the working. So time spent working, you would have accrued a certain income. You use that income towards the different commodities. Any questions about household? It will become more clearer as we move on.
So are you mentioning the commodity? So can you please tell me which type of commodities? The means government authority commodity or the private commodity?
Both
Both. Okay.
commodities could be private or public, but you have to model government very explicitly in this thing. Okay.
Okay.
The next section is the production from industry. Okay. So let's say there is a sugar manufacturing plant. Okay. Now that sugar manufacturing plant needs raw material. It needs fuel, right? It will need diesel or it will need electricity. It will need sugarcane. It will need some other chemicals, and it will need labor, and it will need capital. So those are called primary factors, labor and capital. Sometimes you might need more labor and less capital, or you might need more capital and less labor, depending on the amount of automation. So that is what we call as a share parameter. So you have this share parameter here. It tells you how much you're sharing. The intermediate commodity is energy. So it needs sugarcane. So it needs agricultural. So sugarcane comes from agriculture. So that's an intermediate commodity that goes. You need energy. So that energy can come from electricity, or it could come from diesel, and then so on and so forth. So all of these are like a nested logit. So each part is kind of contributing to an intermediate product, which then goes in. Okay. So commodities and prices. So you have different commodities, you have different prices. So this is so oil is $100 a barrel. So the unit of an oil is in barrels usually. For coal, it is in kgs or tons. So $1.65 a kg. For wheat, it is in kgs, so it's 32 cents a kg. So commodities and prices are a big part of the economy, and they're flowing. They're flowing between industries, they're flowing between industry and households, and not so much between households and industry, but in between industries and industry to household. That's the flow. So we have to give a very, very specific definition of what a commodity is. Commodity is anything that requires, which is used or required to fulfill a household's need, or what people want. We also consider them to be discrete, homogeneous, quantifiable, and infinitely divisible. Okay, so a wheat is a wheat. You might be able to split it out by region. So the wheat from Punjab might be different from the wheat from Haryana. So there are ways of managing that, but the wheat from Punjab is homogeneous. You can't, there's no difference in quantity, quality. They're quantifiable. So many tons are being done from wheat, and they're infinitely divisible. So you can go all the way to 20 grams. You don't have, like, it's not based on, you can only do it by certain tons or anything. They're infinite. So they're continuous variables. Prices are basically relative values of each commodity. So you generally you create a, what you call, you generally have a what we call a baseline price of a certain, we call it a baseline commodity, to which every other commodity's price is relative to. Okay, prices are only positive, and you can only have one price per unit, but that per unit could be defined by region. We'll talk about that, but it is non-zero and has only one price. Any questions so far?
So this economic agent is, I did not get that point. Economic agent is the how we can, means which part is including in this agents.
Agents are anybody who's a decision maker, right, in the model, and who's
Okay.
affecting the. So in our in the CGE model, we have defined it is industries and households.
Oh.
You can also have government being an
Mhm.
agent, where the government is deciding what taxes are going to be there, what that can be also.
Okay. Got it.
Anyone? So for a consumer, one of the things which comes up is when you're consuming, you have different commodities, and generally households consume different shares of those commodities. So, like for instance, one question which you will always face when you're doing these kinds of models is, for a household, which one would they prefer more? 2 oranges and 1 apple, or one orange and 2 apples? The answer goes down to the concept of price, right? Depending on the price, you will determine which one you would prefer more.
Sir, also the need will be also considered.
Which one?
In this example, customer also consider their needs.
Yeah,
Not
their
only,
preferences. So if, for instance,
yeah,
and we'll come to that,
yeah,
and that's what we're going to be talking about here.
okay.
So there are two things. One is preference, so households represent people in the economy, and preferences and utility are the key representation of the households. So let's take an example of two commodity bundles, X and Y. Is X at least as good as Y? Is one of the questions. So we represent this by a utility function, U of X. So utility function tells you that given, let's take two commodities, not commodity bundles, two commodities. Commodity bundles are, if there are n commodities, X is a one type of bundle, Y is a different type of bundle with n commodities. But if there are two commodities where n is equal to 2, the question about utility is which one would they more prefer? So what we usually use is something called a Cobb-Douglas utility function, where we just multiply x1 raised to power alpha multiplied by x2 raised to power beta. And what this means is that if alpha is greater than beta, let's say we are doing it by numbers only. If alpha is greater than beta, that means people prefer apples to oranges. So these parameters are actually alpha and beta telling you a sense of what their preferences are. If alpha is greater than beta or beta, because at the end of the day, utility is, people are trying to maximize their utility. So if alpha is greater than beta, a little bit of change in x1 would actually have a bigger implication on the utility than x2. Does that make sense, what I've just said?
Yes, sir, there will be an example, so you can understand.
We'll do an example this afternoon as well. So
Okay, sir.
about households, right? There are basically three main concepts. One is utility, which talks about preference, which basically captures preferences, what they need, how much they need, what do they like. That's what preferences are. The second one is endowment. So how much wealth do they already come with, right? So households own a vector of commodities prior to entering the economy, which may be sold to earn income, M. So, okay, so that is what endowment is. Then what people are doing, then what we do is, the problem we try to solve is, we are trying to maximize this utility such that this PTX minus M is equal to 0, where PT is the prices, W is the commodities, and this M is the income. Okay, so this is the budget constraint, and within this there is also they come with a certain what you call certain endowment as well. So given a budget constraint, how will a household maximize their utility? So what will be that? The different demand for different products. These are the three main concept for households. So this gives an example of how a household consumer makes this first choice: consumption and versus leisure. So U of H of a household is CH alpha CH multiplied by TH, which is the leisure time, alpha TH. So these are parameters for this. And these two should be equal to 1. Okay.
Okay.
Then there's a nested aspect of it. So CH is equal to CHI beta raised to power beta HI plus CH prime I raised to power beta prime HI. And those two should be equal to 1. And as you go down. Okay. So the two components of the household budget constraint includes a monetary constraint. So this is the leisure time. So the price associated here. So this is the monetary constraint. PK is the price of capital. So this is the amount of capital, right? And PLH is the price of leisure. You add these two up and that you get as PCH, which is the price. So to summarize, with a given amount of time, a sample household agent utility function nest may look like the following. Top nest is a choice between time spent on leisure and time spent on consumption. The second nest is a choice between consumption on products for each industry. And the bottom nest is a choice between consumption on a particular industry in each region. So I might want apples from Himachal instead of Jammu. So that's what this part is capturing by region. All right.
Yeah.
So we have talked about households. What I would like you to take away, I would not expect you to know exactly how it's all working. It's the first time. This is again, the concept of CGE is probably a 1 semester course. I'm trying to put it together to give you a sense of how to do this and what each terminology means, so that once the first time you hear about it, you're not taken back. You're actually able to engage with it and ask questions, and are able to actually then go and read more and and uh, and understand more. Yeah.
Yes, sir.
So firms represent a decision maker of the production process in the industry. All right. So it has two aspects. One is the technology, which is the ability endowed by the firms to transform inputs into outputs. And this production function is represented as a CES function. It's called a constant elasticity of substitution. So like I gave you the example of it, the production depends on diesel and electricity. So what it's basically telling you is that if I had, instead of diesel, if I had more electricity, I would be still able to produce. Right? So this function is telling you, given given all the inputs, you might be able to substitute some of the inputs. And how do we move from that? Does that make sense?
Yeah, it is makes sense, sir, but when we see any practical example or any example, so we can understand more.
Yeah, there'll be an example. So
Yeah.
we'll be doing an I'll send you the files just after this, so that you can take a look at it. Yeah.
Yes.
So the household has a problem of utility maximization. In firms have the problem of cost minimization. They're trying to minimize their cost. Because if they're trying to produce some amount, they're trying to minimize their cost. The way they try to minimize, so for an output, to produce an output, y is equal to fx. So they have to produce this. So that is a constraint. They're trying to minimize the price associated, some of the price associated with each of the commodities which are going in as an. So this defines the demand function for the firms. Any questions?
So, sir, in this all this firm and customer, we are only see the producer, right? So, hello, sir.
Yeah.
So in case how we know how is the attraction of this all this model or the community.
Sorry, can you say that again?
Currently we see the the production whenever the production will be happen and what the reason regarding, right? So how we can analyze whenever the attraction is going and what are their criteria means accordingly to the production.
Okay. So the way to think about it is a bit different than what you're used to in the production attraction sense in demand modeling.
Okay.
When I'm talking about production and firms and producers, this is literally industries which are producing sugar.
Okay.
Right?
Yeah.
So if they're producing sugar, what is the amount of intermediate goods they need? So this, I'll not go into the details of this, but what this basically says that for a production of YF, it is basically equal to the minimum of the. So basically, it's constraining based on what is the minimum input of each. So if there is a certain amount of diesel which is there, which is the constraining part of my production, then I can only produce, even if I have lots of sugar, I can only produce because I have limited diesel. That's what this formula is saying. It is taking the minimum, so each one is an intermediate input, right? And there is a factor associated to how much does it actually contribute to the production. And minimum of this will be the actual production of that commodity. Okay.
Yes.
So this is the capital aspect of it. So XP F by pi F is the capital share.
Okay.
The primary factors. If you don't have enough people, you can only produce, which gets limited to that. So this is to summarize. Firms of profit maximizers, as stated earlier, firms earn zero economic profit in an equilibrium because the supply is equal to demand. There is no concept of profit. They are using up everything. Hence, production levels are determined from market equilibrium. Each firm's production is a function of their available technology, which is used to formulate their production function. So a sample firm production function might be split into two components, human labor and human capital. Okay. And intermediate inputs which are going in from other sectors. Right?
Yes, sir.
So this is how a market would look like. So you have a commodity and the supply is P1, with different prices. And because of that, there's a demand for it. So this is the supply and this is the demand. Where P1 is $2, P2 is $4, P3 is $3 each. So the question is, how much will it need? And this is where your concept of equilibrium comes in. Households and firms are assumed to be price takers. That is, no direct control over the prices because the market is deciding the prices. It's not any one government or any one company that is determining the prices. And for each given price vector P, there's an excess demand. In a market is the difference in the amount demanded and the amount supplied. So what we are trying to do is we are trying to find the prices in our network such that this demand minus supply is equal to 0. So this is the demand and that's the supply.
Yeah.
That is it. So there are two major aspects. One is commodity flow. The second is monetary flow. So the households provide labor. That's a commodity. They provide capital to the production, to the firms. They also, from a time perspective, they also consume leisure, which is part of their utility. Production produces goods. The goods are used again within production. The goods then are consumed by the household. Sorry. Then you have monetary flows. So the firms will pay for the capital. They'll pay a rental rate. They pay a wage rate to the labor. And income is equal to expenditure, which is basically from the consumption, right? Which they are paying to the goods. And the production is paying for goods again. So they're paying money. So this is basically telling you how the money flows. So the money flows opposite to the goods and labor and capital. Any questions so far?
So can you please go for previous slide?
Yeah.
So in this household or production, we did not consider the travel time or travel cost for monetary flow, or only considering the capital or investment.
Can you say that again?
So in this means you say, sir, we consider in household time and capital. So how much income and how much expenditure we have to go to the firm. So accordingly, we did not consider the travel cost.
Yes, that's good. That's so the way we actually include. So there are two places where that comes in: travel costs.
Okay.
Here we have assumed that there is leisure and there is labor, right?
Okay.
So time can be spent, but we can also include travel time.
Yeah.
Okay.
Yeah.
The second thing is when goods are consumed for production as intermediate, they have to go through roads, rail.
Right.
So there is a cost associated to logistics here,
Hmm.
which they are consuming.
Right.
So money will flow to that also.
Okay. Got it. So this also consideration. Okay.
So that's what we had to build a Sydney network for this. So you have firms. You have firms in households, the CGE model, and then you have the transport network model. So the transport network provides the travel time and travel cost, and the firms will determine how much commuting, shopping, leisure, freight is happening on this. And what we are doing is we are doing an iterative CGE transport model where we run the CGE model, then the cost from the transport model come here, then we run the CGE model, then it gives me new ODs. It will give me new origin destinations. I'll run the transport model, get the costs, and we just iterate until it converges. So this is just giving you an example of what we did for. This is just an example problem.
Okay, so this all things we are doing in Emson or any another software. So
it's another software.
Okay.
So it's a tool which you have to almost build from scratch.
Okay.
So this is the travel time savings. So let's say that we want to increase the capacity on link 6.3, okay, by 50%. That is basically adding one more lane. So the travel time savings from that came out to be only $71 million. But the wider economic benefits was $47 million. So it's not only the travel time savings, but people's jobs, the income, all of that was $47 million. Now, when we reduce the travel time on this link by 50%, we have bigger, wider economic benefits, and even larger when we build a new link. Now, the wider economic benefits include, because we have made these links, we have reduced the travel time, it has reduced the logistics costs. And because of that reduced logistics costs, the price of the commodities have come down, right? The moment the price of those commodities comes down, it makes it more affordable. So more people can actually, the demand increases because the price has gone down. So more people can consume it. So that is also incorporated in the wider economic benefits. Okay?
Yeah.
This is the second one where we actually had to build out a wider WestConnex. WestConnex is a new tunnel, which was at that time in 2011, they were planning, there were different stages. And we did an evaluation across all of these for the M5 widening. So the reduction in travel costs manifested in both increases in household leisure time and increases in labor hours. Because the moment you're able to reduce travel time, people have more time. So what they're able to do is split it not equally, but split it by a certain ratio toward leisure and labor. So that is an increase in their, it's not just travel time, value of travel time savings, it's an actual increase in their utility. It increased in the welfare as well. The largest beneficiary being residents in residents and producers. And there was some, so you can actually look at impacts by different regions as well. So these are the different regions. And so you can see what are the impacts from a EV. So EV is equivalent value, so equivalent variation, which is basically telling you how much income has certain regions have improved. So region 3 has had the maximum benefit for scenario 3, which was, so it was scenario 3 was having M5. So that's M5 plus WestConnex stage 1A. So it's this one. So it was M5 was there, and you're adding this widening of the. But there are some regions which actually don't do so well. So they have there's a reduction in value there. but it didn't matter because this part of Sydney that the people are quite. When I say that doesn't matter, um, they are quite wealthy in that region. So from a fairness and equity standpoint, it was making sense. So this is a comparison across the different regions. So scenario 6 provided the maximum benefit to the maximum people. So what was scenario 6 here? So you have the M5, you have the widening. So you do all of these together, you end up with the maximum benefit across a wider region. Any questions?
So for a scenario preparation, we are considering the peak hour traffic or any another consideration, or because in general things means what I do in microscopic analysis or micro
You
simulation
you do peak.
yeah
So
for this also
here we
same
are
or
doing so generally we take morning peak for the commute because it's commute
okay.
traffic.
Hmm.
Yeah, that's what we are doing.
Oh.
So any questions?
Mm. No sir. No.
So you guys we can take a break and we'll reconvene in the at in a few hours um, for the tutorials.
Yes sir, sure. So
Okay.
so one request, are you share with your PPT with us, no, sir?
Yeah. I'll share the PPT with you.
Yeah, actually yesterday PPT we did not.
Yeah. I think I have shared it. It just needs to be PDFed, and I think it's with the team. I've sent it.
Okay sir, okay, thank you.
Thank you.
Hello, Vikas sir. Vikas sir. So when is the next class? Will be around 2:30 or 2 p.m.?
No, to
Okay,
2:30.
okay, okay, sir. Okay.
In fact, if we have some time, do we have some time right now? Okay, so what I can also do is I can take this opportunity to share uh, the use case which we did for India.
Yes, sir. It is.
And so I think that those are slides which have been shared with you. Have you seen those slides?
Yes, sir.
Yeah. So I'm going to, can you see? All right. So if we look at the CGE models, right, with currently the reason why we are looking at developing CGE models for India is because of Gati Shakti, as well as comprehensive logistic plans which are being developed as part of the smart city program. So logistics cost is a big piece which we are trying to reduce. And freighting takes both time and money. So how can we actually incorporate that to demonstrate wider economic benefits? That's what it was. So we have built the largest CGE model in the world with 33 states, 29 industries. So that means 33 multiplied by 29 multiplied by, so the OD table is 33 cross 29 cross 29 cross 33. So that's the number of cells which are there. So what happens if the today's rail network was made 25% faster? That was one question. We also have done stuff with DFC, which we have published a paper on as well. So this gives you the modal demand for the base scenarios. So what was happening in 2021-22? This is giving us the freight based off. This is for the rail, and this is for the road, right? It's giving us
Yeah,
a percentage. So, for instance, there's a higher percentage of road freight in Maharashtra and Madhya Pradesh. Okay, but a higher percentage of freight on rail from Karnataka, Tamil Nadu areas. That's basically based on data which we have received.
okay, sir.
So if we upgrade the network, right? Upgrade the network to by increasing reducing the travel time by 25%. What will happen? What we observe is, if you look at this area, this was the road. Maharashtra had a very high road percentage, right? Very high road percentage. That has gone down. It goes down closer to 90%, like closer to probably 88% instead of the high 90s. And the rail percentage also increases. So it has increased a little bit to 20% or so. So you can actually look at making these shocks in different parts of the net on different parts of the network and see what really happens. So this tells you what the total freight demand was, the change in freight demand for different types of modes.
If possible, sir, can you please tell me which software we can use for this CG modeling purpose?
So we have had to develop so the lot of the software is built in Python. You have to actually code it up.
Okay.
And so there are softwares which we have built out, so we can talk through that as well. So we're going to Jason will be speaking about it this afternoon.
Okay, sir. Got it.
So you can look at impact on the prices for different commodities. So this is what will be the prices, the percentage change in prices for agriculture and allied activities in different parts of the country. Right. So Gujarat had a big reduction in agriculture and allied activities because of increasing the increasing the speeds on railways. You can do a full analysis like this, and it helps you understand what the impacts on commodities by region is, what is the impact on GDP, what is the impact on different metals, etc. So yeah. So the next, we are actually developing even larger model with all the districts and industries as well. So with that, we can stop for now, and we can meet later this afternoon.
Yes.
Okay. Thank you. Thank you.
Thank you, sir.
Thank you. A walkthrough with an example of how these are built out. So over to you, Jason.
Hey Vinayak, do I have control of the screen at the moment? Because these are not my slides right now.
Yeah, you do. You can actually share the screen from I'll shoot. I can.
There's some slides at the moment that's being shown, but these are not.
Yeah. So you can actually go.
Sorry, give me a moment. Hey, Vinayak, sorry, let me just look for these slides.
Jason,
Thank you, Professor Vinayak, for
yeah.
giving.
Jason,
Yeah.
can I just give you a call? Just give me, if you don't mind, we can just have a chat offline. Just give me 1 second. We'll just.
Yeah, sure. Sure thing.
Today's tutorial, what Jason will be going through is the examples of how we develop, like the different steps of developing a CGE model through this example.
Yep. Thanks, Vinayak. Can everyone see my screen? Yep. Okay. Cool. Excellent. I believe Professor Vinayak's gone over the basics of what CG modeling is this morning. So as he mentioned, now what we're going to do is to look at an example of such a model. So this particular model, the link is in the chat room, so feel free to access the link and download the model itself. So this model is a small example we prepared for this demonstration. Now, when you open it up, you'll see there's a bunch of different folders and a bunch of executable files. Now, most of these executable files are on the back end, so there's no any need to run them. So the main two executables that we'll be looking at is the ones on the bottom, the run model executable, and the run model shock executable. These two executables take all the other executable files and all of these folders and use them to produce results for the model itself. So all of the equations, all of the data that Professor Vinayak went through in the morning, all of that is all in these other folders and files. But as a user, when we're using the model, there's no need to open them up. Really, all we need to do is just access these executable files. So just as a quick demonstration, if I were to run the model, it'll open up a screen, it'll do a bunch of calculations, and once it's done, it'll go through this process of running the model. So I'm just gonna stop it for just a moment here. So here you can see there's a bunch of output messages in the command prompt window. These are only for the programmer to look at. As a user, you won't need to really understand any of the information that's coming out of this console log, because once the model has finished running, all of the information we need as users, all of the outputs are going to be located in the outputs folder here. Okay, so if we open up the outputs folder and go again, this will show us all the results of the model run. So I'm just going to terminate the model prematurely here. So you can see these are some of the temporary results from the model. So because of the way this model works, it gives us the answer by going through what's called a general equilibrium seeking process. So this process takes many, many iterations of the code. So you can see here, we've got results for the iterations in this folder. If I were to let the model run to completion, so if I were to go back and if I were to double click the executable file and leave it and let it run for maybe 50 minutes, maybe an hour, when it finishes running, the window should close by itself and gives us the final results in this folder here. But for demonstration purposes, the intermediate outputs here during the process of finding general equilibrium, you can find all the results here. Okay. Is there any questions so far as to what we've just seen? No questions. Okay. So again, very straightforward. For the model we've prepared, as a user, all you really need to do is just to run the model. You don't have to worry about any of the equations, any of the data. It just goes by itself. Okay. Now, in terms of interpreting the outputs, let's have a look at an example of an output. So many of these outputs don't really make much sense to us.
Okay, if you don't mind, Jason, can I put a prompt in there? Can we go, if you don't mind, talking a little bit through the input data, like because we did talk about like essentially in a CGE model, we end up having the households, we have the firms, and we have the network as well. So if you can just kind of walk them a little bit through the idea of the input-output data and how it currently looks in this, that'll be great. If it's
sure thing. So in terms of the input data, most of that could be found in this model in the calibration data folder here. If you open up this folder and go again here, you'll find a couple of CSV files here. So these CSV files are the input files for this particular model. So as an example here, so these are all coded. So the names here are coded. They don't mean much for us. But let's take a look at an example. So this R file, this R.csv file represents the regions of our model. So in this particular model, R is the regions of India that which we are modeling. If you open it up, you'll see that there's a couple of numbers here. So these numbers don't really mean much just by itself. However, the way we read these numbers is that each region in India is given a code. So here there are 3 regions. The name for these regions is just region 2, region 0, and region 1. This is a 3-region model. We pretend India is 3 regions. And so therefore we give them the names 0, 1, and 2 for computational ease. And we put them in this file called r.csv, meaning regions of India CSV file. And it's just 0, 1, and 2. In a more complex model, in the large model that we've built, there are a lot more regions. So as an example, if we were to construct a model for India using states and union territories, there will be 30-something regions, right? So you have 30 numbers here instead of just 3 numbers. So really, it just depends on how many regions you want in your model. You can change it around by defining them in these files here. Similarly, there are other things here like I.csv. I represents the industries within the model. So you can see here there are a lot more industries here. In fact, there's 28 industries from 0 all the way down to 27. We just call them industry 0, industry 1, industry 2, so on and so forth. In actuality, each of these industries has a name associated with it within the national accounts. So as an example, Industry 0 is actually the agricultural and allied activities industry within India. However, again, because this is code, this is on the back end, we don't write it using text. We represent it as a number just to make the code run a little bit smoother. Likewise, 1 is the forestry and logging industry, 2 is the fishing industry, so on and so forth. Every single one of these numbers corresponds to an industry, to an industry sector within India's economy. Does that make sense? Any questions? No? Cool. Okay. But as you can see, right, files like the industry file and the region file gives us information as to what the model's scope is, how many regions we have, how many industries we have. In terms of the actual economics data, we can take a look at a couple examples here. So one, yes, did someone want to say something?
Yeah, I wanted to actually just add a little bit more on the idea of calibration. So the one of the things to remember is that if you remember when we were talking about how the household utility model how are we representing household utility, or how are we representing industries, right? They have all these parameters, but we need to estimate these parameters based on the data. And that's what calibration does, is based on all this data, it tries to solve the simultaneous equations as a set of simultaneous equations to give you what the parameters are. So now you have a calibrated model that represents the economy of today. Then what you do is you can add in a scenario and compare to what that would look like tomorrow. So, thanks. Over to you, Jason.
Yes, thank you, Vinayak. Yes, Professor Dixit is absolutely correct. The purpose of having all of these data is to allow us to estimate how the economy behaves. Okay, so to be more specific, this file here, this IOGH file, this represents all of the trade that happens within India. So if I open up this file, you'll see a bunch of numbers here. This doesn't really make sense to everyone here, but what this effectively is calculating, is recording, is all of the trade that happens in India between industries and between regions. So for example, the amount of, let's say, iron ore that's sent between regions within India, that's recorded in this data set. The amount of bread or apples or petrol that's being sent between regions in India is recorded in this data. Now, the issue with this data set for a model is that just knowing how much bread or how much apple is being sent between regions is not actually enough for us to figure out how the economy behaves, right? Because in the future, let's say in 5 or 10 years' time, these numbers are going to be slightly different because the population will change, because people's preferences change, the economy changes over time, right? So just knowing these numbers doesn't give us any information about how people behave in the future. So the calibration process is what allows us to use this data to figure out parameters that estimate how people behave in the future. And so that is recorded not in the calibration data folder, but in the base data folder. So again, calibration data is all of the raw numbers that we've just discussed. The parameters that Professor Dixit just mentioned, which explains how people behave, that's in the base data folder. So if I open it up, you'll see here, this looks a lot more different. You've got these, variables called alpha, there's betas, there's gammas, right? And if I open them up, these numbers, again, don't make much sense. But essentially, what these numbers do in the base data folder is explain how people and how businesses behave in the economy, which means that we can use this to estimate what happens in the future if changes in the economy happens. Okay, so again, calibration data is the economy today. Base data is information about how the economy might behave tomorrow. Okay, and so given that information, we can then model scenarios like Professor Dixit mentioned, if the interest rate goes up, if the tax rate changes, if we build a new road, if we create a new trade deal with a different country, all of that will change the economy, and we use the parameters in the base data folder to estimate what that will look like using the CGE model. Any questions? No questions. Okay, excellent. But that's what the executable files do here. So what the executable files do is it's actually a 3-step process. The first step is to take the calibration data, the raw data files, and use them to estimate the parameters in the base data. That's the first step. The second part of the run model executable is to use the base data parameters and validates them. So it takes those parameters and then runs a couple of tests to make sure that those parameters are suitable and they match what we expect. And then the third part of the executable file is for testing future changes to the economy. And that third part is where the bulk of the use of CGE models are. In that third step, when you're testing how the economy is going to behave in the future, that's when you as a user can come into the model and insert information. So for example, if you want to know how a trade deal with the United States is going to change the economy, you come in on that third step, put in the necessary data, and then run the model. If you wanted to see what happens if the tax rate goes down by 0.5%, you come in on that third step, put in the data, and then run the model. Okay, so again, first part of the model, second part of the model where you run the calibration data, where you test the base data, that does not require any input from you as a user. It's only that third step when you're testing scenarios for the future economy, you come in and you put in that data. Does that make sense, everyone? Is there any questions? No? Okay, cool. Yep. Yes? No? Okay. Vinayak, did you have anything to add?
Oh, there was something. I thought there was somebody who wanted to ask a question, so that's why.
Yes, I thought so too. But...
No, all good. Can we go through an example of a scenario analysis? Like I think there was one scenario you had created on this.
Unfortunately, the data is hard coded, so I cannot insert the data as I wish. Yeah.
All right. Okay. So can you talk through the outputs a bit, if you don't mind?
Yeah, sure thing. So so this is the outputs folder. If you remember, all of the outputs come in here. So a lot of these outputs require you to be familiar with the data in the model here. So for example, this is the aggregated cost of freighting commodities between regions in India. If I were to open that up, right, these numbers is the cost if I wanted to ship iron ore between any two regions within India. So these numbers are all here. However, as a user, it'll take some studying of the model itself, of what these numbers mean, before you understand how to interpret them. So an easy one that we can look at, for example, is something like the commodity price, right? This is the price of a commodity, the price of a good. So here, this lists all of the expected prices of the commodities within India. The price of apples, it's here. The price of iron ore, it's here, right? Now, again, these numbers by themselves don't mean all that much, but what we can do is we can use these to perform a comparison. So this is the cost of commodities that we expect the model to produce. Now, what we can do is, if you remember, right, there's two parts to the model. There's the first part where you calibrate the model, where you use existing data of the economy today to figure out what the behaviors are going to be. So what you can do is you can take the estimated prices of our commodities and then make a comparison with today's prices to see what's going to change. So I can perform an example here. So for this example, I've set the prices of all of the commodities to just one. Okay, this is just an example. In reality, these numbers will be different. You'll find data for it. But for this example, the prices are all one. You can see that the model is predicting that the prices are going to change fairly significantly. There are some decreases. So for example, this first entry is decreasing from 1 all the way down to 0.337. This one's decreasing a little bit down to 0.67. Whereas in other industries like this one, the prices are going up a little bit. Okay. Now, again, the interpretation for this is not within the scope of the tutorial because this really depends on the data that you have. But for our purposes, what this does is show us that using the model, we've got some expectation of the economy today, and we can use it to figure out what the economy might look like tomorrow. And here you can make a direct comparison. You can see, for example, oh, the prices of apples within Andaman Nicobar has gone down, but the prices in apples in, let's say, Mizoram has gone down a little bit less than that, So these are the sorts of analysis you can do. And of course, this is only one data set. This is the price of commodities. What we can also do is look at values like the GDP of the country. So that's calculated here in firm production, right? You can compare production of today with production of tomorrow. So I can open up an example here. Right, you can see here changes in production. So here it's much less than the changes in prices. However, if you go through the list and go through the numbers and look at the changes, you can figure out all of those changes from these results. Okay. Any questions? No? Okay. Vinayak, was there anything you wanted to add on that?
Nothing from me, Jason. But I'm hoping there would be questions, or can we, if you don't mind, once we do the calibration, we end up with like parameters, right?
Yep.
Can we? I think there was a question this afternoon about like let's take the alphas were the, if I remember, I'm trying to remember this. Alphas were the ones for the households, correct?
That's correct.
Yep. So, and alpha underscore C was for capital or for consumption, and alpha underscore T was for leisure.
Yes.
So can we just kind of open up that? Let's open up alpha underscore C. So can we go through like a let's take the first row, if you don't mind, and can
Well,
we?
this is just a measure of the preferences for consumption in a household.
From
So
different.
the thing is, these parameters are, if we wanted to explain what every single one of these parameters are, we can do that, but there's documentation for this sort of stuff.
Yeah.
But essentially what this file, as an example, does is explains how much people living in each part of India prefers to spend their time. So this number ranges from between 0 to 1, where if the number is 0, it means that the people in that region, they don't want to work at all. They just want to spend all of their time for leisure. Whereas a number of 1 means that they want to spend every day, every minute of their day working, and they want to spend no time for leisure. So that's what this number is meant to represent. Of course, no one is going to be 0 or 1. It's usually a range of values between it. The larger the number, again, the more people prefer to work over leisure. The smaller the number, the less people prefer to work compared to leisure. And so here you can see a lot of these values are 0.5. This is a default value we set because for a lot of these entries, it's not, how do I describe it? For a lot of these entries, either we don't have enough data to make a calibrated parameter, but for this model, more to the point, is that a lot of these entries are not necessary. So this particular model was built to be used for a very large model of India. Since we've made it so that there's only 3 regions, a lot of these entries are going to display strange behavior like this. But the important thing is that the values here mean something much more abstract. So this does not mean the amount of apples or the amount of petrol. It's really just how much do you want to spend your time working versus leisure, right? This is not something that's recorded by the data. No one goes out and surveys people like that. So really we have to estimate these values based off of our calibration data. And all these examples here are similar to that. So gamma here, gamma is the preferences that people have for different regional commodities. So this number, for example, if I were to sell you an apple, do you prefer apples in Delhi compared to apples in Maharashtra compared to apples in Mizoram? So this number is supposed to represent that preference. It's the same product, but where you buy it from, does that matter to you a lot? 0 means that it doesn't matter. 1, it means it matters a lot. Okay, but that's all these parameters are. They just describe how people behave in the economy, what their preferences are, from small to very large.
Perfect. Thanks a lot. Thanks, Jason. Any questions, guys? Anything you'd like us to discuss?
Hello.
Hi,
Hello,
Manish.
yes.
Yes.
Yeah, I have one question. You say we do a calibration, right? So in calibration, can we use a regression to prioritize our this all this thing? Means that Excel sheet that you coming
So
as a final
let
output.
I'll take that. So essentially, that's pretty much what when we do when we double click calibrate, it's
Mhm.
it's it's not doing regression so much as you have a set. You remember when we were doing equilibrium, we were
Mhm.
doing a set of algebraic equations and trying to solve for it. This
Yeah.
one is basically doing that. We have all these parameters around, like when you remember the Cobb Douglas function we talked about. So we had the Cobb Douglas function. So in the Cobb Douglas function, we have these parameters alpha and beta. So we have all these equations which we discussed, such that you have the uh, market equilibrium conditions where the supply is equal to demand. So when you
Mhm.
have all these such equations you're solving for equally, like it's simultaneously, that's when you're able to generate that. So the calibrate is actually just doing that.
Okay. So
If
in
you
this
want, I
case,
can add something on top.
Yeah,
Sorry,
please
Manish.
go ahead. So no,
So,
please.
so that comment, thank you for the comment, but the comment about regression leads me to believe there might be a slight implication here we haven't discussed. So in CGE modeling, the calibration is not statistical. There is no statistics involved in calibration of CGE models. When you talked about regression, right? Regression is a statistical method. So as an example, if I picked someone at random and I ask them, do you prefer to work or do you prefer to take leisure? That person may have a probability of high probability of wanting to work or a low probability of wanting to work. So if I pick any one person and ask them that question, then yes, we might have to regress their preferences. But the thing about CGE models is that it is an aggregate model. We are not looking at one person or two people. We're looking at the population of India. We're looking at all of India. And usually what we observe when aggregated is that there is really not much point to doing statistical methods for some of these, for these aggregate level economic analysis. And so therefore, when we calibrate, we don't do any sort of regression modeling because we accept that at these large levels, statistical methods tend towards the expected value anyway. So therefore, we just do this in an analytical method. We, like Professor Dixit said, we have the simultaneous equations, and then we just solve for those unknowns rather than trying to statistically estimate them. So there is no regression involved here.
okay, sir. But in calibration, can we prioritize anything, or we can just calibrate our whole data? For example, we are calibrating the Maharashtra state road network. So in that, we have prioritized the arterial, sub-arterial road in this category, or throughout the network we calibrated in a single model.
Let me take that. So Manish, the idea of prioritization does not happen here. It is just a system of equations which we are solving to get the results. Now, we can develop the model. Uh, we can specify the model to either include uh, smaller roads like regional, like residential roads, or we focus on the larger roads like arterials and national highways. So it really depends on the type of analysis you're doing. Usually, we don't in the CGE model. It's a macro model, right? So in a macro model, you're only interested in looking at the important roads. So when you're building your network, it's the important transport links that you build out.
Yes, got it.
Yeah, perfect.
Thank you.
Any other questions?
Vinayak sir, are you sure in previous slide that you are showing in the final output we see a graphical representation? So can we see that graphical representation from that JSON's data as a final output?
Oh, the graph. So like the shape files, like looking at, so one of the things, Jason, I was showing them was the India model where we could look at the 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 shape file and what was the impact. Because this is a small model, we generally would do a graph analysis. So we couldn't, because it's these 6 regions are not really have a shape file. I don't think we created a shape file. We just have links between these regions. So you can literally, because you have only 3 or 4 regions in this. How many? I think, was it 3 regions?
It was 3.
3 regions. We have only 3 regions. You can literally do a bar chart for each of them.
Okay, sir.
I think to answer the question is, yes, we can produce a map like Professor Dixit showed. It is possible, right? If you remember, one of the files we showed was r.csv, which was the regions in India, right? So as an additional step, once your outputs have been produced, you can take the outputs and then also take the shape files for India and then combine the two into a map like the one Professor Dixit showed you. But like he said, we haven't done it for this example because there's only a couple regions. A map isn't really useful, but definitely it is something that can be done if you really want.
Any other questions?
I think sir, no.
Okay. I think that's all we have for today, actually. Then, if
So the general question I ask, so
yeah,
how many times required for Jason to develop in such this model? I know he doing his PhD on it, but it's 1 year or 2 years or more than that.
oh, so I'll allow Jason. I think that's a question for Jason more than me because he developed it. I'll just give an initial thing. So when you're developing the first time, it's always hard, um, but it might be much quicker for Jason to do it now. So hand it over to Jason.
Yeah, thank you, Vinayak. The process of developing a model, the bulk of the time really is understanding all of the equations that's really used. Because if you don't understand the equations, you won't really know what data to gather. So that part it took me a couple months to wrap my head around the process of the equations and where the data might fit in. That took a couple months. Once that part is done, the next most difficult part is the collecting of data. Now, for India specifically, this question is more difficult than for other countries like the United States or Australia, because in India, a minor problem, it's a relatively major one for the model, but is that a lot of the statistics, a lot of the data is not available in a central manner. So what I mean by that is, if I wanted to, for example, know people's consumption habits, right? In Australia, our census collects all of that data very thoroughly. So it's very easy for us to get that data here. Whereas in India does have a census. It does have a household consumption expenditure survey, but the data there is very quite limited, right? We know how much people pay for their petrol, pay for their food, but there's not much information on how much they pay for their insurance, right? There's not much information on how many hotels people go to, if any. So because there's a lot of missing data, there was a lot of time spent trying to figure out what those numbers might be. So that process for India took probably about 2 years, 2 years or 3 years. But that's because we kept coming up with ways of finding those numbers and then figuring out they weren't working. It was really just a back and forth process. We imagine that in the future years, once India's statistical capabilities begin improving, and they are improving, but once they get to a level where they have all this data centrally collected, the time is going to become much, much faster.
And also, once you have the first model, all right, like things become much, much easier. I remember when we developed the first traffic simulation model for India, it was really hard. But then it became easier because people understood. You start improving ways of getting data and all of that. But yeah.
Yes, sir. Got it.
Any other questions? All right. So I think what we'll do is we'll stop for now, and happy to discuss. The next. Any other questions? As promised, tomorrow I will do an example on safety, the highway safety model.
Sorry, sir. Last question I have.
Yeah.
As you mentioned that we have collected the data from India for various agencies. So how can we means rectify that data we collected are uh, right or wrong, or that will be properly applicable for our models or not? Because there will be a lot of checks we have to be implemented in that model, because it is a huge model. It is not a one day work. No.
Can you say that again? I'm not able to understand. Sorry.
So how can we validate that data is right or wrong? Is that data we get from the various agencies from India? So how can we know that data will be proper or not? Means there will be any misunderstanding or any incorrection in that.
So as Jason, it's a very valid question. As Jason was mentioning, that probably has taken us 2 years itself.
Yeah. Okay.
So it's a big problem. But the thing about it is that is always going to be an issue when you're developing such a model for the first time.
Yeah. I got it. It is. I know it is a big problem in every country, not for India, for every.
And specifically when you're building it for the first time.
Yeah. Yes, sir. Thank you.
Thank you. Sounds good. Anything else? All right. I'll thank you, everyone, and we'll take it. Thank you very much.
Yes, sir. Thank you. Thank
Thank
you, Jason.
Thank you. Thanks, Jason.
Thank you, Vinayak. Thank you, everyone.